All right, folks. So I thought, so the previous section we were talking about periodic variables. So it was 2.68 in the book. And at the end of the chapter, he touches on the idea of these these wrapped distributions. And I thought, um, well, let me back up. So basically, when I read that section, you might recall that the way we defined the von Mises distribution was to take a 2D regular normal, bivariate normal distribution, and then condition on being on the unit circle. And that seemed like a bit of a weird construction to me, perhaps to you as well. And I thought, well, what would happen if we just took a normal distribution and then wrapped it around a circle just over and over again? So what would that distribution look like? That probably occurred to some of you as well. And it turns out that this is actually a thing. It's called the wrapped normal distribution. People don't use it as much because I think it's a bit harder to work with than the von Mises distribution that we saw in this section. But this derivation is, I think, really simple. So I thought it'd be really fun to go through, and it has some kind of nice properties that I just thought were cool and I wanted to share with you. So think of this as an optional section. It's not in the book, but it might be fun. So I thought maybe, yeah, it might be fun to go through it together. Okay, so what we're going to be talking about is periodic variables and what's called a wrapped normal distribution. Okay, so what's that going to be all about? Well, the idea is that we already know how to work with normal distributions, right? So here is let's make it a bit. So here's a normal distribution. Let's say we have a normal distribution. And it's going to be without loss of generality. Let's have it mean 0. So here is x equals 0. And we're going to have this thing. And you have to assume, you have to just imagine that's symmetric. I drew a nice, and this is just going all the way to infinity and to minus infinity. Okay, so now that's going to be defined on the real line, right? So x here belongs to R. But now we want a distribution over the circle. So a natural thing might be to just wrap this thing around the circle. So the idea would be, let's call this, on the real line. So now wrapping it around the circle. So all we'll do is we'll just kind of take chunks of it and just wrap them around a circle of radius 1. So all we'll do is we'll just now have a circle, and the idea will be that and I will kind of draw the distribution. So maybe it kind of looks like this, and then it kind of goes out, and then it kind of wraps around again. So a particular value here, for example, at that, let me just color that in. It corresponds to that value, but then it corresponds to, let's call this x1. So you'll get x1, but you'll also get x1 plus 2 pi, x1 plus 4 pi. All of those probabilities will add up at that location, and the same for every other place. So that's kind of what we mean by wrapping. So essentially, like taking, these chunks of 2 pi, let's say 2 pi, and just kind of wrapping them around the distribution, and in both directions. And so what kind of probability distribution are we going to get in that setting? So let's have a look. So the idea will be, so we're going to have, we'll call it, instead of without having to use indices and stuff, we'll just call it Q. So Q will be our distribution on theta. So we'll say Q, so the probability of our data falling from theta to theta plus d theta, and theta is just going to be a number between 0 and 2 pi. Well, we're going to say that, well, that's the same as the probability of, and p I'm going to use for this normal distribution, of, let's say, x equals theta, just to be very explicit, to x equals theta plus d theta. And we're going to assume that things are scaled so that d theta measures the same length as dx. Okay, but it's not just that, right? There's going to be, this is where the wrapping comes in. So it's going to be plus x equals to theta plus 2 pi, and x, so this is, and x being equal to theta plus 2 pi plus d theta, and so on. And and including the other direction as well. So p, x is equal to theta minus 2 pi, x is equal to theta minus 2 pi plus d theta, all the way. Okay? So q we don't know. We're going to build it up from p that we do know. Okay, so now what are all these things? Well, as you make d theta very small, well, this is just going to equal to, the sum. So we've got k is going to equal to minus infinity to infinity. So the k is going to be the index of the two pi's we're adding. So p of x is equal to theta plus 2 pi k. Right, so the probability mass in that section. And well, what is that? Well, this is just equal to, so that's just going to be, when you make the d theta is very small. So p of theta plus 2 pi k d theta. And what do you have on the other side? Well, you've got, it's going to be q of theta, our density, times d theta. And so the d thetas will cancel out. So let's just cancel them out. So now we get q theta is going to equal to the sum of p of theta plus 2 pi k. Okay, so, all right, but what does that actually look like? So that's kind of the very first instance. We've got this kind of wrapping thing happening. And now this p, well, that p is just our normal distribution, right? So just, I'm going to drop the minus infinity to infinity stuff. So that's going to be 1 over root 2 pi, and this is the variance. And we're just going to have and remember our mean was 0, so it's just going to be theta plus 2 pi k squared over 2 sigma squared. Okay? So now all we're going to do is we're just going to expand that out. So this is going to equal to, again, the sum on k, 1 over root 2 pi sigma squared times the exponential of theta squared plus 2 pi k squared plus 2. So the 2 is going to multiply the 2 pi, so it'll actually be 4 pi k theta. And all of this and all of that over 2 sigma squared. Okay, and now what can we do? So we can actually we can simplify some things, right? The summation, the summation here is over k, so we can remove that contribution out, and we'll just end up with this funny thing. So let's do that. So this is going to equal to, let's move all the things we can to the outside, and we're going to have an exp minus sigma squared over 2 on the outside, and then it's going to be this sum, this interesting sum. And so then on top we're going to have 2 pi k squared plus 4 pi k theta over 2 sigma squared. Okay, now I don't know, what is this sum? So we're going to ask Mathematica. So let's go ask Mathematica. So we're going to, let's go and do this together. So I'm going to switch here. Okay, cool. So you should be able to see this. So let's move some of my coffee around. Okay, all right. So here we are. Okay, so we want to integrate this sum. So and you guys can all see that. Terrific. So sum on exponential of minus, and this was what? This was 2 pi k squared. That doesn't look very nice. Plus 4 pi k theta. Okay, and all of that over 2 sigma squared. And we want this evaluated, so the sum over minus infinity to infinity. Okay, and it immediately comes back with something that looks interesting. Okay, so let's now, I'm going to write that down. So let's go back and I will, okay, so now we have gotten that from Mathematica, so it's going to be exp minus sigma theta squared 2, so that's what we had before. And now Mathematica tells us that there is, the result of that sum gives us a x theta squared 2 sigma squared. There's also a sigma term that shows up. There's also a factor of root 2 pi that shows up. And then there is this like elliptic theta 3 theta, and the theta is theta function, so that's a different theta, of course, whatever we're going to call that, at theta over 2, and the other parameter is e to the minus sigma squared over 2. Okay, so but there's already some interesting cancellations that are happening, so let's cancel. So this cancels that, this cancels that, and what we are left with is 1 over 2 pi times, elliptic theta, the third, number 3, whatever that is. Okay, and now to figure out, well, what is this function? Well, we go to, let me switch again. So if you go to, for Math World, we see that the function actually has this really nice form. So it's this guy down here. So I'm going to now, you can see that one, right? So I'm going to now switch back and copy that down. So now what we get is, well, this is just going to equal to 1 over 2 pi of 1 plus 2. And now we have this sum going all the way to infinity. Now our q, so there's some q parameter, well, that's just this guy. So it's going to be e to the minus sigma squared n squared over 2. And then there's going to be a cosine, and after we kind of cancel some things out, it's just going to be cosine of n times theta. Okay, so that's it. So that is our function. Okay, and so what first let's check a couple of things. So does it integrate? So we need to check, does it integrate to 1? So let's make sure it does. So we need that d theta from 0 to 2 pi, the cyclical variable, it must equal to 1. Okay, well, if we actually look at this, well, all of these terms, this is for, oops, and this should actually be not n. Let me fix that. So that should be k squared, k theta. There we go. Okay, so all of these cosine terms, because k is greater than 0, all of these terms, when you integrate them, so all of these are going to integrate to all this stuff is going to integrate to 0, right? Because you just have a cosine function that you're integrating. You're not squaring it. It's just a cosine function integrating over, multiplied by some constant term, integrating over 0 to 2 pi. That's going to be 0. And there's just this one term that integrates to 2 pi. So indeed, so this is going to integrate to, of this is going to equal to 2 pi. And so the 2 pi here cancels the 2 pi there. And indeed, we get that it does integrate to 1. So that's good. The other thing you need is q of, oops, let me switch colors. So is q of theta greater than or equal to 0? That one you actually have to show us. It's not quite obvious from this that it is, because let's have a look. So this guy, so this is going to be, it's going to belong to minus 1, 1, and it's getting multiplied by 2. So this term in principle could go from minus 2 to 2. When you add 1 to it, you get minus 1 to 3, which there might be a chance of getting some negative value. So it will turn out that you don't get those, but you have to show that. So it's not obvious from looking at this that those values are actually going, at least not obvious to me, that those values aren't going to be negative. But I don't think they are. So I think this is well defined, and it is well defined. So, but you just have to show that. So let's just say we'll just say exercise for reader. Okay. Cool. So that's so that it has the basic properties of a probability distribution. And so the only thing I wanted to kind of point out about it is it's actually got quite a cool form. And it's got a cool form because you can think about it. So let me just erase all of this stuff. So I mean, at first it was pretty easy to derive. So let's just copy it down so we can play with it a bit. There it is. Okay. I'm just gonna. Okay. So this is what we have. So what's cool about it is that you can think about. So you might know, like if you worked with Fourier series and Fourier transforms, that a normal distribution, if you take its Fourier transform, so if you try to express it in terms of sines and cosines, complex exponentials, a normal distribution on a real line, its Fourier coefficients are also Gaussian. So you have a kind of a bell curve. We take the Fourier transform, it also has a bell curve. So one thought you might have would be that when we're going from the real line, so this is R, and now we're going to the unit circle, that maybe something similar happens. So here we have, we're going to have, we're describing a normal distribution. So, and the normal distribution is symmetric. So we're going to, the things that we're going to be, the Fourier components are going to be, cosine, 2 pi kx, where k could be kind of any real number, because that distribution is not periodic on the real line. So you can say, well, maybe what's going to happen here is when we go to the unit circle, well, first of all, we're going to have cosines. But now these k's are going to be integers. So these are going to be belong to the integers. So k belongs to z, theta. And maybe the coefficients will also kind of have that kind of Gaussian, that Gaussian shape. So you can imagine that you've got these cosines and all their harmonics, and you can say, well, by analogy to what happens on the real line, where a bell curve transforms into a bell curve, maybe what happens on the unit circle is that the corresponding coefficients, which will now be corresponding coefficients of just particular cosines, because we have a periodic shape here, they will also have Gaussian coefficients. And indeed, we see that that's exactly what happens here, right? Oops, didn't mean to erase it. So indeed, you can think of these, these are the coefficients. So these are your Fourier coefficients, right? The Fourier coefficient of a series this time, because you have this periodic structure. But these are exactly, this is exactly a bell curve, right? Except the bell curve with the variance of your distribution now showing up as the precision, which reflects that, like when you go from the real to the Fourier, Fourier domain, if something that's narrow in the real domain is going to be tight in the Fourier domain and vice versa. So that's why your variance is now showing up as the precision in, as showing up at the top of these coefficients. But yeah, and essentially what you see is that, again, we're dealing with integers now, but if we kind of plot these terms, they kind of, at k is equal to 0, well, k equals to 0 corresponds to this, and they're kind of just falling off. We don't have, so this is going to be, they're falling off with 1 over sigma squared. So you get kind of a very nice, like if you had thought about it in those kind of Fourier terms, you get essentially the analogous, essentially the thing you would think of. Maybe you get some of the factors here wrong, but it's essentially the same idea. You have a bunch of cosines reflecting the fact that we have a symmetric distribution. It's symmetrical around 0. The k's are integers because we have the function is periodic, but the coefficients, just like in the other case, the coefficients are the former bell curve. So it's pretty. I thought it was, it's a pretty cool connection that way. Yeah, so I just wanted to kind of share that with you. Now, I guess it turns out I haven't worked with the wrap normal distribution, but I guess it turns out that like it's a bit hard to work with, so people tend to I guess tend to prefer the von Mises distribution. It turns out also the von Mises distribution has some other useful properties. For example, as we'll see, I believe, when we talk about the exponential family, that the von Mises distribution becomes the maximum entropy distribution when you kind of know some aspects of your data. I forget which. We'll cover it there. So it turns out the von Mises distribution has kind of some better properties, and it approximates this wrap normal in some settings. But I thought this was kind of a cool derivation, a simple derivation, and has kind of some very nice analogical properties that I want to share with you. So anyway, so that's the wrap normal, and now you've got at least two distributions you can think about when you're working with periodic variables. So I hope you enjoyed that, and that you'll join me in the next video. Bye.